Hello guys, welcome to this video. So you do realize what day it is, right? It's World Quantum Day on 14th April today. So I didn't know about this, but I just recently came to know that 14th April is World Quantum Day, and I just thought I would make a video on quantum mechanics, a sort of presentation. So please watch it if you like, and if you are new to the channel, please subscribe, and that's all. Let's begin. Okay guys. Yeah. So World Quantum Day, 14th April 2022. So in today's presentation, I will take you through the journey of the journey of physics from classical physics to quantum physics. We will not be discussing the modern physics like particle physics, information paradox, and string theory and quantum gravity, but because that will make the video very long and it's not possible for me to discuss. Maybe we'll discuss it in some other videos in some other day. So today our focus will be on quantum physics, the basic quantum physics, and philosophical interpretations of quantum physics, quantum entanglement, and quantum mechanics, and so on and so forth. So let's start without any further delay, and a happy World Quantum Day to you all once more. Classical physics and determinism. Classical physicists were confident that the world could be studied and understood with Newton's and Maxwell's laws. So what are Newton's and Maxwell's laws? There are some laws. Newton's laws of motion, they govern the motion of bodies, of macroscopic bodies rather, and Maxwell's laws are the laws of electromagnetism. They govern the electromagnetic behavior. So at that point of time, Newton's laws also describe gravitation. That's one of the fundamental forces of nature. So, and Maxwell's law describes electromagnetism, which is also a fundamental force of nature. So classical physicists at that time, by the way, there are four fundamental forces of nature, but at that time the other two forces, weak nuclear and strong nuclear, were not known. So the classical physicists believed that these Newton's and Maxwell's laws were enough for the complete description of reality. Classical physicists held that the universe is like a huge machine which runs according to the laws of classical physics. Complex behavior can be understood as a result of the simple behavior of the machine's inner parts. They also believed that motion takes place due to some reason. Everything has a cause. They also believed that energy in motion could either be represented by a particle or a wave, but not both. Finally, they also believed that it was theoretically possible to measure to any degree of accuracy the properties of a system. I haven't mentioned one of the most important beliefs in classical physics yet. So this is very important. This is what I mean by determinism. If the state of motion of an object, that is the state of motion is just the position and momentum of the object, is known at one point of time, say now, it could be determined at any point of time, any other point of time in the past or the future. Nothing is uncertain. And if we could somehow know the states of motion of every particle in the universe, we could predict the state of motion at any given time. I mean, it's theoretically possible. Practically, no. But this idea is theoretically possible. And this idea is known as determinism. Many scientists like Pearson and Laplace caught what I call the Newtonian fever of absolute certainty. However, with the advent of quantum mechanics, it would become clear that determinism is false. So a word on free will. This is not strictly relevant, but still I decided to include it in the presentation. There has been a long debate between those who support free will and those who support determinism. So some people say that even today, in light of quantum physics and modern physics, you may say that deep down the world is deterministic. So determinism, some people still do believe in determinism. And I'm not saying that's a bad thing because we can't say anything for sure. But the supporters of free will suggest that there is no determinism and the future is not predetermined. But this is a very delicate point. Michio Kaku says in The Future of the Mind, ultimately I think free will probably does exist. But it is not the free will envisioned by rugged individuals who claim they are complete masters of their fate. The brain is influenced by thousands of unconscious factors that predispose us to make certain choices ahead of time. If you know a bit of neuroscience, you will know this thing. That most of our lives will run unconsciously. We make choices unconsciously, even if we think we made them ourselves. This doesn't necessarily mean that we are actors in a film that can be rewound anytime. The end of the movie hasn't been written yet. So strict determinism is destroyed by a subtle combination of quantum effects and chaos theory. In the end, we are still masters of our destiny, but maybe not complete masters of our destiny. Opening the doors to new science. Classical physics had to give in finally. Classical physicists had to open the door to a new science, quantum mechanics. So let us begin by taking up the case of a black body. So we will be discussing what a black body is very soon, like in the next slide itself. So experiments on which for the first time revealed the incompleteness of classical theories. The need for an entirely new concept was felt. That turned out to be the quantization of energy into discrete packets called quanta. What do you mean by quantization? That means you're breaking anything, like here it's the quantization of energy. You're breaking anything into discrete packets, like it's not continuous. Like energy cannot radiate continuously, but in discrete packets called quanta, singular quantum. Thus, quantum theory was born. At the beginning of the 20th century, few people realized that quantum theory would evolve to be such a revolutionary theory. It would give rise to earth-shaking technologies as well as earth-shaking paradoxes. It would give birth to grand unified theories that would come tantalizingly close to the ultimate unification of the four fundamental forces of nature, and finally string theory, which may indeed after all achieve Einstein's and the physics community's long-desired dream of grand unification. Quantum theory has changed science, redefined everything fundamentally. It's not merely a theory, but a scientific revolution. So blackbody radiation and Planck's quantum. A blackbody completely absorbs and emits all electromagnetic radiation. Electromagnetic radiation is just the light that is falling on it. Of course, a 100% efficient blackbody cannot be realized in practice, because a blackbody, a body that completely absorbs all the radiation without any sort of reflection, and it completely emits all the radiation, so that 100% efficient, that's not possible in practice. A small opening, that's a cavity in a blackbody, will give off radiation emitted by the walls. At high frequencies, conventional theories predicted that an infinite amount of energy is radiated, which is obviously false, because it's like, see, a small opening or cavity in a blackbody will give off radiation emitted by the walls. This point is clear. Now, at high frequencies, conventional theories predicted it's not a linear relationship. It's a like as the frequency increases, soon the energy soon the energy blows up to infinity, sort of infinite amount of energy is radiated. But this is not the case actually. If we have a black body and if we have a small cavity, so in no case infinite amount of energy comes out. If infinite amount of energy comes out, that means it is possible for the black body to completely destroy everything. Of course, that's not possible. So this is referred to as the ultraviolet catastrophe. The classical theories failed due to the application of the law of equipartition of energy. Planck showed that energy can't be divided infinitely. Energy is not continuous and cannot radiate randomly, but in discrete packets called quantum, plural quanta, directly proportional to frequency. So this was the crucial point. Energy is directly proportional to frequency. Energy E is directly proportional to frequency, and E equals hf, where h is the Planck's constant. So this equation describes the energy of the radiation. More appropriately, it's E equals nhf, where n is the number of quanta. This means that the total energy is just the total number of quanta. Problems with classical theories. In earlier times, it was generally believed that a body radiates or absorbs energy continuously or spontaneously. The energy dependent on the intensity. This was what classical wave theory said. The energy of light, for instance, dependent on the intensity. However, it's a common observation that on heating an iron rod, its color changes. So color means what? For specific particular wavelengths, we have particular colors, and wavelength is related to the frequency. So if the old theory was correct, then increased heating should only change the intensity of the color, right? The intensity of the color, the brightness of the color, but the color shouldn't change, because if the color is changing, that means the energy is depending on frequency. The fact that the color changes too shows that energy depends on frequency and thus wavelength. With increased energy, the frequency increases. At high frequencies, as E is proportional to F, the quanta are so large that only a limited number of vibration modes are excited. Now, it's not possible for me to go into the mathematical treatment of this thing, but yeah, that's just a basic idea. So as at high frequencies, the classical theories predicted ultraviolet catastrophe, infinite amount of energy. But if you are dividing energy into discrete packets called quanta, the advantage is that the quanta are so large at high frequency that only a limited number of vibration modes are excited, and the radiation drops off to some finite value, and thus the ultraviolet catastrophe is avoided. All this clearly showed that classical physics had some serious problems. It was evident that a new science was coming. The photoelectric effect. Just like Planck defined radiation to be consisting of small packets of energy, what if light is also assumed to have a particle nature? What if light is just a stream of particles? This idea was very radical at the time it was proposed by Einstein, when light was widely believed to be an electromagnetic wave. The wave theory of light successfully explained a lot of phenomena. Einstein, however, went forward with this idea and proposed the particle theory of light. That is, light consists of quanta hf called photons. He named the quanta photons. Photons are just the quanta of light. The particle theory also explained some phenomena like the photoelectric effect. It has been observed that if light is shown on a metal plate, electrons are ejected. This means light consists of particles which transfer energy to the electrons, and on gaining this energy, the electrons are able to break free of the surface of the metal plate. So whenever you're shining light on a metal plate, some electrons are ejected. So this means light consists of particles which transfer the energy to the electron, and on gaining this energy, the electrons are able to break free of the surface of the metal plate. So light beams can eject electrons from a metal plate. However, electrons are ejected only if the frequency of the incident photons is greater than the minimum threshold frequency. If the frequency is exactly equal to the threshold frequency, the electron will just be ejected from the atom. However, the frequency is greater than the threshold frequency, then the extra energy becomes the kinetic energy with which ejected electron will move. So there are a few things like which the wave theory of light could not explain. Actually, the wave theory of light could not explain, because you see, just give me 1 second. I think my system has hanged, which is very common nowadays. Yeah, anyway. Okay, all right. The photoelectric effect. Okay, yeah. So see, the light is falling on the metal plate and the electron is being ejected. So there is no time lag between these things. There is no time lag. So what does this suggest? This suggests that if light was a wave, so first of all, the wave should come and some time must be needed, some time must be spent to transfer the energy from the wave to the particles. But since there is no time lag, it actually supports the particle nature of light. That light consists of particles, and these particles called photons, and these photons directly at once transfer the energy to the electrons. Then this threshold frequency concept, if the wave theory of light was correct, then there should be no threshold frequency. If the surface is heated for long enough, then electrons should evolve after some time. But if the frequency is less than the frequency of the incident light is less than the threshold frequency, no matter how long we shine the light on the metal plate, no electrons are ejected. So all this was a support for the particle theory of light. But we must not forget that the wave theory explained many phenomena, like Young's double slit experiment. So it explained the wave nature of light, the interference pattern, the diffraction, and those things. So we cannot say that the wave theory of light is mistaken, the wave theory of light is false, nor can we say that the particle theory is false. So today it is assumed that light has dual nature. Light has both wave nature and particle nature. So today we assume that light has dual nature. Atom essentially means something which cannot be divided further. Ancient philosophers believed that if we go on dividing matter, we would soon reach such a fundamental unit that it couldn't be divided further. Some scientists initially thought that all this was useless, since there is no way to carry out observations and measurements at such scales. And at that point of time, some scientists believe that science is all about observation. Science is all about what you can observe and what you can measure. But as we will discuss later in today's video itself, some things cannot be measured, but those things are important enough to be included in science. So we should broaden the scope of science. Okay. However, the study of atoms and beyond would soon reveal a very different and bizarre world down there. Atomic spectra. Atomic spectra is simply the spectra of frequencies of electromagnetic radiation or light emitted or absorbed during transitions of electrons between energy levels within an atom. So within an atom, there are basically many energy levels, and electrons can jump from one energy level to the next. So, and while electrons are jumping from a higher to a lower energy level, it is giving off some light, because when it is at a higher energy level, it has some energy. When it is going to a lower energy level, it is releasing some energy, and this energy is being released as light, as photons. And if it's jumping from a lower to higher energy level, it absorbs a photon or a light energy, electromagnetic radiation, and it gains the energy, and it becomes excited, and it moves to the higher state. So each element has a characteristic spectrum by which it can be recognized, just like you can be recognized by your fingerprint. Atomic spectroscopy provided strong evidence for the quantization of energy. So spectral lines form due to electron transition from a lower energy level to a higher one, absorption of photon and thus energy. Or the opposite, emission of photon. I explained this thing just now. So a hot solid emits white light containing all frequencies. When it is passed through a slit and a triangular prism wedge, a continuous rainbow-like spectrum is obtained on the screen. For a hot gas, we get a bright line spectrum, that is some specific lines at some specific frequencies or wavelengths, where the shape of each line is the image of the slit. So in this case, we don't get a continuous spectrum. All the frequencies are not covered. This is because the angular momenta of the electrons of the angular momenta is I hope you know what a momentum is. Momentum is mass into velocity. That's the classical momentum. But angular momentum, it's the counterpart of classical momentum in rotational mechanics. Like when a particle is undergoing rotational motion, circular motion, it has the angular momentum. So the angular moment of the electrons which are orbiting the atom, electrons of the gas, they are quantized and all frequencies are not allowed. We will see this later. So every line corresponds to a specific transition corresponding to a specific frequency. If a cool gas is kept between the slit and the hot solid, we get a dark line spectrum, that is absorption spectrum. This means a continuous spectrum with the missing slit-like dark lines corresponding precisely to the bright lines in the case of the hot gas. So I didn't have much time to put together this presentation, or it would have been better if I put some images so that you can understand. But the thing I'm trying to say is that for a hot solid, you get a continuous spectrum, like a continuous spectrum, rainbow-like continuous spectrum. All the frequencies are covered. For a gas, for a hot gas, you get some lines, some disjoint lines, some vertical lines. Only some particular frequencies are covered. Now, if we put the cold gas between the slit and the hot solid, then we get the continuous spectrum, sort of continuous spectrum, except in those portions where there were the lines, in the bright line spectrum, in those portions where there were the vertical lines, precisely those portions will be dark. There will be no color on those portions. That means the continuous spectrum with the missing slit-like dark lines corresponding precisely to the bright lines in the case of the hot gas. So note that the same element is being used for all the cases, as different elements have different bright line frequencies. So what is happening here is that the cool or unexcited gas is absorbing light at precisely the same frequencies at which it emitted light when heated. So when heated, when it is emitting the light, but when it is cool, it's absorbing the light and it's absorbing it at the same frequency. Because only at those particular frequencies we are not getting the lines. We are getting the dark lines at the precise places of the bright lines. There must thus be certain characteristic energy states in a gas which can take in or give off energy. So here are some earlier models of the atom, like Thomson proposed an atom where the negatively charged electrons are embedded on the positively charged proton containing base. Neutrons were not discovered then, the model was discarded. Ernest Rutherford carried out his alpha particle scattering experiment where he bombarded the alpha particles, that is helium-2+, on a thin gold foil and found that most of the particles could penetrate it. So this was determined by zinc sulfide plate. Sparks on it meant the particle has penetrated by the gold foil. Thus he reasoned that most of the atom is empty space with a dense, tiny, centrally located nucleus. Electrons, he assumed, revolved around this nucleus in circular orbits. But Rutherford's solar system like a nuclear atomic model was also discarded due to the fact that negatively charged electrons moving in circular orbit around the positively charged nucleus are accelerated and should collapse into the nucleus. So the concept is that just like a static charge gives rise to electric field and a moving charge gives rise to a magnetic field, an accelerating charge gives rise to an electromagnetic wave. So if an accelerated motion, I hope you're aware of this, that accelerated motion, whenever a particle is moving in circular motion, even if it's moving at a constant speed, its motion is accelerated because it's changing the direction continuously. Velocity depends on the direction as well as the speed, right? So that means this electron should emit electromagnetic radiation. If the electron is emitting electromagnetic radiation, if the electron is giving off energy, then the electron should collapse to a lower energy state, and so soon the electron will be attracted and collapse into the nucleus. This should have been the case. But that means everything should have collapsed. Stable atoms could not form in the first place. Our world could not form as we know it. So the nucleus, also if it were the case that the electron was continuously releasing energy, then the spectrum should be continuous, which is not the case. Okay. Bohr's atomic model. Bohr, who had also significantly contributed to the study of atomic spectra, came to the rescue. Although Bohr's atomic model is no longer accurate when quantum mechanics comes into play and has been replaced by the wave mechanical model, but Bohr's model works good for a single electron systems like the hydrogen atom. The more accurate Bohr-Sommerfeld model describes the atom in terms of elliptical orbits and explains certain phenomena like Zeeman effect, etc. Arnold Sommerfeld proposed that electrons move in elliptical orbits. However, even this model was not entirely successful. So let's get to the basics of Bohr's model first. In Bohr's model, electrons move around the nucleus in distinct energy levels or shells or orbits, KLMN. They were just named KLMN. So electrons will fill up higher shells only if the lower shells are completely filled. On gaining energy, say photons, electrons can jump to a higher energy level but can usually remain there for a tiny period of time, decaying back to its original state, emitting the captured energy. The tiny centrally located nucleus contains protons and neutrons. The mass number of the atom is the total number of protons and neutrons together called nucleons present in the nucleus. The number of protons, which is equal to the number of electrons for a neutron atom, is the atomic number of the element. So all this is chemistry. I will not go into this. But the thing I'm trying to say that the Bohr's main postulate was that electrons move around the nucleus in distinct energy levels, and even with the electron is undergoing accelerated motion, when it is moving in this distinct energy levels, it does not radiate energy. So we can get around the problem that Rutherford's model had. So the quantization of angular momentum, we will be coming to that after de Broglie's idea, the quantization of angular momentum. So that is very important postulate of Bohr's model. But before that, the nature of light. The nature of light has been controversial for ages. Waves or particles. On one hand, we have particles which form a notion of distinctness. If a particle occupies a position, no other particle can simultaneously occupy that same position. On the other hand, waves form a notion of continuity. And we know that more than one wave can exist at the same point, interference. Both the wave and particle theories explain certain phenomena. Newton believed that light was made up of corpuscles. However, this particle nature of light failed to explain interference and diffraction. Now, when I say particle nature of light, I refer to Newton's idea, because I'm not referring to Einstein's particle nature of light, because Newton actually believed that light consists of particles which had some mass, elastic collisions. But Einstein's theory says that light consists of particles called photons, which has only relativistic mass. So both are not same. Though I'm calling the particle nature of light, but they're not the same thing. And anyway, in Newton's day, we didn't have great insights into the nature of light. So that was just a rough idea. When Maxwell found out that the electromagnetic wave and electric and a magnetic field vibrating at right angles to each other, propagating in vacuum, had the exact same velocity as that of light in vacuum, it was accepted that light has wave nature. Phenomena such as diffraction, interference, etc. could be best explained by the wave theory of light. But Einstein reintroduced the idea of particle nature of light by proposing the idea of discrete quanta of light, photons, to explain the photoelectric effect. Ultimately, as per modern quantum mechanics, light has dual nature, as I've already told you. Light has neither particle nature nor wave nature exclusively. Light can act like both particles and waves. Bohr believes that it all comes down to whether we are using a wave detector or a particle detector. This is the basic idea behind complementarity, which formed an integral part of Bohr's philosophy. De Broglie's idea. De Broglie proposed that the idea that everything must have a particle as well as a wave character. So not just light, but everything. So light has a dual nature, but de Broglie said that even everyday matter which is supposed to have particle nature, even they should have a wave nature. Just like light, which is supposed to have wave nature, should have a particle nature as well. So he proposed, so this is the idea of pilot waves, or a wave that accompanies the particle through space and time, and that has a phase velocity and as a whole packet a group velocity. A particle which is localized in a small but finite region wouldn't in quantum theory have a definite velocity, but will have a set of values. Such a particle would be described by a wave packet traveling with a group velocity equal to the average velocity of the particle. So we don't need to get into this too deeply, because these are just theoretical ideas. I'm just trying to give you the basic. I'm just trying to communicate quantum physics to a broader audience. I have tried to do this in my previous videos also, but if you are new to the channel, and especially as today is World Quantum Day, so I thought of making this video. So de Broglie gave a relation h over p equals lambda, where h is Planck's constant, p is the linear momentum of the particle, and lambda is the de Broglie wavelength associated with the particle. De Broglie's relation is a simple yet extremely important relation in quantum theory. This formula holds not just for photons, that is light, but for all particles. In general, all particles must exhibit dual nature. Although this dual nature is not prominent for macroscopic objects. For everyday objects like a ball or a bottle, you don't see the wave nature. They appear particle nature. They appear distinct particles, distinct objects. So the wave nature of particles will be felt when the probe into the particle is over regions compatible to the wavelength associated with the particle. That means very small probes, very small. For microscopic particles, very small particles, we can see the difference. For daily life macroscopic objects, the wavelength is negligibly small to give rise to any perceptible wave-like phenomena. The quantization of angular momentum. Bohr assumed that the angular momentum of an electron moving around the nucleus is quantized. So just like we saw the quantization of energy by Max Planck, Bohr said that the angular momentum is quantized. The angular momentum of an electron, MVR, must always be a whole number multiple of the reduced Planck constant, h by 2 pi. H by 2 pi is also called h cut or h bar, whatever you say. So MVR is the angular momentum, mass into velocity into radius. So MVR equals nh cut or nh bar or nh by 2 pi, where n is a whole number. So the angular momentum must be a whole number integral of the reduced Planck constant. So this means when an electron changes orbit, that is come to the third paragraph, when an electron changes orbit, that is jumps from a lower to a higher orbit, when it gains energy, that is photons, hf, or from a higher energy level to a lower energy level, when it emits energy, its angular momentum MVR always changes by some whole number times h bar. Angular momentum always changes by some whole number times h bar, not randomly, not continuously. The angular momentum of electron is thus always quantized. Thus only orbits that are whole number multiples of h bar can exist in Bohr's model. These orbits are called allowed orbits. Now interestingly, you can easily derive Bohr's formula for angular momentum for an electron of mass m moving with velocity v around an orbit of radius r from the de Broglie relation. You can try it. So I will not be doing that here in today's video. But this is not how Bohr came to this conclusion, but de Broglie showed this that Bohr was correct by using his theory. Okay, uncertainty in quantum mechanics. Matter has a wave nature, so they are spread out over some distance. What is the position of a particle within the wave? That depends how you measure the position of the particle. You will find the particle at some definite location, but if you measure it again, you will find the particle at a very different location. And this is not due to any experimental error. So like it is a wave nature. So if you're trying to locate the particle, what is the position of a particle in the wave, you will find that it has no definite, no fixed position. Once you're measuring it, it will appear to be here. Next time you're measuring it, it will appear somewhere there. And this is not due to any experimental error. Repeated measurements will display a statistical distribution of locations. After de Broglie proposed the wave nature of matter, the idea quickly emerged that because of its wave character, a particle's trajectory and destination can't be accurately known for each particle individually. However, each particle goes to a definite place. After compiling enough data, you get a distribution related to the particle's wavelength and diffraction pattern. So there is a certain probability of finding the particle at a given location, and the overall pattern is called a probability distribution. What quantum mechanics does is predict the probability distribution in various circumstances. So the idea I want to convey through this is that there is some uncertainty in quantum mechanics, which gives rise to the Heisenberg's uncertainty principle. That is our next slide. Okay. The double slit experiment with electrons. In the double slit experiment, a beam of electrons is passed through two slits and a larger screen is placed behind. Though it seems obvious that the most probable location for finding the electrons would be the areas on the larger screen directly behind the two slits, though some electrons may get deflected through an angle. This is not the case with electrons. So you have two slates, two very thin slates, and you're passing electrons, bombarding electrons, let us say. So if electrons were just particles, then they would just pass through the slits, and most of the electrons will be found directly behind the slits. Some electrons may be deflected by a small angle, but that's it. But though this may hold true for macroscopic objects, this doesn't hold true for microscopic objects like electrons. The electrons pass through both the slits simultaneously and interfere. That means the electrons have a wave nature. The electron waves, when emanating from the slits, bend and become circular if the width of the slit is small enough, diffraction. So when we have two emanating waves forming at close proximity, as both the semicircles radii go on increasing, the waves will interfere and form a striped pattern. The waves interfere the most in the area directly between the two slits, and that is the most probable location for finding the electrons, not the area just behind the slits. So Heisenberg's uncertainty principle, the world was satisfied by the Newtonian explanation of the universe. Some people like French scholar Laplace were seized by the dream of an absolutely certain universe. Laplace believed that if the positions and momenta of all the particles of the universe are known, then in principle it becomes possible to predict the states of these particles at any time in the past or future. This is the idea behind determinism. Determinism, along with objective, observer independent reality, locality, that is, objects can be influenced by one only by direct contact, causality, effects can't precede the cause, that is, nothing can reach or exceed light speed, and continuity, no discontinuous jumps in nature, form the basic assumptions of classical physics, and all of them are challenged by quantum mechanics. However, Heisenberg's uncertainty principle has proved that it is impossible to determine with 100% certainty both the position and momenta of even a single particle, leave alone all the particles in the universe. So this proves that determinism is false. Even for a single particle, it is impossible to determine both the position and the momenta with 100% accuracy. Both the errors in energy and time cannot be simultaneously known for a particle too. So this holds for energy and time and position and momentum. The error in position multiplied by the error in momentum must always be greater than or equal to h cut over 2, h bar over 2, and the same holds for the product of the errors in energy and time. To determine the position of a particle, consider a microscopic particle here. One must shine light on it. To locate a microscopic particle like an electron, we need a high energy, that is low wavelength light, so that it can interact with the particle. But then, being a form of energy, it will affect the momentum of the particle. So you get it. Okay. The master forgets his own theory. Einstein tried to challenge the uncertainty principle. He imagined a box of light. A single photon could, in principle, be released from the box by a clockwork shutter. So this was a thought experiment. I thought I would include it because it's very insightful. The exact time can be recorded. Like we have a single photon in a box of light, just for the sake of thought experiment. He imagined a box of light. A single photon could, in principle, be released from the box by a clockwork shutter. Thus, the exact time can be recorded. Also, the box can be weighed before and after the photon is released. Finding the change in mass using E equals mc squared, the energy of the photon can also be known. So, using the clockwork shutter, we can know the exact time, the error in time, and we can know the exact time with 100% certainty, and we can also know the energy because The box can be weighed before and after the photon is released, and we can finding the change in mass, we can use E equals mc squared to find the energy. So don't we know both the energy and the time accurately at the same time? No. Enter Bohr, defender of quantum theory. As Bohr pointed out, Einstein overlooked the fact that when the photon would be released, there would be a recoil. However small, there will be a recoil, creating an uncertainty in the position of the box in Earth's gravitational field, which ironically from Einstein's own theory of gravity, theory of general relativity, would create further uncertainty in the time. This uncertainty principle is 100% accurate, Heisenberg's uncertainty principle. Although Einstein will later question the completeness of quantum mechanics in the E-pair paper, and not even Bohr could find a satisfactory solution this time. The E-pair paradox still remains a hotly debated topic in science. I will discuss it later on in today's video itself. So the original E-pair argument was this. If one measures the position of one of the two coherent electrons, that is electrons belonging to the same quantum system, the wave function of the entire system would collapse into one of its position eigenstates. Position eigenstates refer to the set of values for the position, instantly revealing the other electron's position. So suppose these two electrons they belong to the same coherent system, same quantum system, and they're coherent, but suppose that is the different thing, that they are light years apart. I'm not discussing that here. Let us focus on this argument here, the original E-pair argument. So once more, if one measures the position of one of the two coherent electrons, that is electrons belonging to the same quantum system, the wave function for the entire system would collapse into one of its position eigenstates. So instantly it will reveal the other electron's position. Measuring one electron's momentum similarly would reveal the other electron's momentum, meaning the other electron should have both these quantities ready, that is existing at the same time, violating the uncertainty principle. Because the second electron cannot possibly know in advance which quantity among position and momentum the person may choose to measure. It's my choice. I can measure the position and I can measure the momentum. So if I measure the position, the other electron's position gets revealed. If I measure the momentum, the other electron's momentum gets revealed. So how can the other electron know whether I'm going to measure the position or momentum, right? So it should have both the position and momentum ready, sort of. This is just a very basic idea of the argument. I'm not going into the rigorous argument here. Okay. So what is quantum mechanics? Richard Feynman famously remarked that anyone who claims to understand quantum mechanics actually understands nothing of it. This quote has been hailed by many people to justify incorrect claims. What Feynman meant, in my opinion, is that although physicists know how to use quantum mechanics, they don't understand what quantum mechanics is telling us about the fundamental nature of reality. You can use the computer, but it's very likely that you don't exactly understand everything about how the computer works. So quantum mechanics, simply put, is the mechanics of tiny particles at the atomic scale and beyond, deeper. Science has grown strange from the days of Newton. It was from time immemorial assumed that the best way to understand the world is to focus on the pieces, to figure out how these pieces fit together. This approach is known as reductionism. But the quantum reality we live in cannot be understood that way. The reality as described by classical physics is only a rough approximation of the actual reality. Even quantum field theory is supposed to be a low energy approximation of a deeper unified theory that we are yet to discover. At much higher energies, all the forces are unified. So here are some basic postulates of QM. I know you will not get everything if you're new here, then new to quantum mechanics. I know you will not get everything, but just by me reading out some paragraphs, and so it's not possible like that. But I think you will get the general idea, and that is what I'm trying to do for the World Quantum Day, nothing more. So in classical physics, we assume that all dynamical variables describing a system can be measured simultaneously. Like we said, determinism. However, in quantum mechanics, dynamical variables take a set of values, sometimes continuous like position, or sometimes a discrete set like angular momentum. Angular momentum is discrete, I already discussed. Quantized. Position can be continuous. Space is continuous, after all. We don't know whether space is continuous because we treat space as continuous. Like a particle can be at any position in the space. Obviously, according to new theories like loop quantum gravity and everything, maybe space is itself discrete and space is emergent also. So that's a different thing. As a postulate of quantum mechanics, the result of a measurement of any dynamical variable in a system is one of the possible values allowed for the variable. So there are some possible values, and when you are measuring it, the result of the measurement must be among those possible values, cannot be anything other than that. Also in classical physics, measurement is supposed to be carried out with any disturbance in the system tending to zero, that is without any disturbance. In classical physics, measurement is supposed to be carried out with any disturbance in the system tending to zero. However, in quantum physics, results of a measurement cause a collapse of the system from a superposition of all possible states to a distinct state. Like in quantum physics, the very act of measurement interacts with the system, disturbs the system. So when a measurement is made on a system for a dynamical variable p and a value small p is observed, the state of the system immediately changes into one where the dynamical variable p has the value small p. Quantum tunneling. Everything, no matter how strange, is reduced to probability by quantum mechanics. You must have heard of things like the possibility of a prisoner escaping through the prison walls. The probability for such things to occur in the case of macroscopic objects is negligible, almost zero. But at the quantum level, everything is different. A particle without enough energy to pass over the potential barrier may still tunnel through it. It is impossible in the case of a hypothetical infinite well, for even if penetration occurs, the width of the well walls is infinite, so the particle cannot make it through. But the tunnel effect does occur in finite wells. For instance, alpha particles emitted by certain radioactive nuclei. An alpha particle whose kinetic energy is only a few megaelectron volts is able to escape from a nucleus whose potential wall is 25 megaelectron volt high. The probability of escape is so small that the alpha particle might have to strike the wall as many as over 10 to the power 38 times. The phenomenon of alpha decay beautifully verifies the counterintuitive predictions of quantum mechanics, quantum theory. The quantum tunnel effect has important applications in the semiconductor industry, for example in Zener diodes. So why can't we walk through walls? Yes, theoretically we could walk through walls. You can even get stuck within the wall. So how are we to walk through walls? It all depends on probability. Quantum mechanics allows tunneling, theoretically. A particle, if bombarded toward the wall, has a very less but non-zero probability of ending up at the other side of the wall. But if a human body is to tunnel through the wall, each and every particle would need to tunnel all at exactly the same time to the other side of the wall. To start with, the probability of single particle doing this is unimaginably small, because even for a single particle, the probability that it will tunnel through the wall is extremely small. Like we saw, right, that it might have to strike the wall as many as over 10 to the power 38 times before it emerges on the other side. And for a human being to walk through a wall, all the particles should tunnel all at exactly the same time. So the probability of all the particles of a complex body doing this is almost zero. Also, the particles must do it at the same time if you are to end up in a good condition on the other side. That's also one point. The wave function. Schrodinger developed an equation that gives the solution to the wave function of a particle. The wave function, denoted by the Greek letter psi, is a mathematical function which has no physical significance by itself. The square of the wave function, that is the product of psi and its complex conjugate psi star, gives the probability of finding the particle at a given region of space. So psi into psi star, that is psi squared, mod psi squared, that is the probability of finding the particle at a given region in space. That has the physical significance, but psi by itself has no physical significance. Psi is the wave function. The wave function can be expressed as psi equals a plus ib, which is a complex number basically, where a and b are real functions and I is the imaginary number. The complex conjugate psi star of psi is given by a minus ib. The square of the wave function, that is psi into psi star, is a square plus b square, because I square is minus 1, so ultimately we're getting a square plus b square. So psi square is always a positive and real quantity. Of course, probability can't be negative. From the study of waves, it is known that energy is directly proportional to the square of amplitude. In the wave mechanical model of the term, psi can be treated as the amplitude for the electron wave. Psi square thus gives the probability of finding the electron. This is obvious, since if the amplitude of the electron waves is maximum at some region, it means that the energy is maximum there. The presence of energy invariably points to the presence of the electron itself. Thus, in that region, the probability of finding the electron is maximum. Schrodinger's wave equation. Schrodinger was not happy with Bohr's old quantum theory. He believed that the atomic spectra should be determined by some kind of eigenvalue problem. He came up, eigenvalue problem, I made this presentation from my notes on quantum mechanics, and there I have described eigenvalue problems in a later stage. So that's why I have written see later. But right now I have, like, for today's presentation, I have nothing to offer for eigenvalue problems. Like I will not be explaining eigenvalue problems, but it's not possible to explain everything in quantum mechanics in a single video. Anyway, so he came up with the revolutionary equation, the famous Schrodinger wave equation. Once Schrodinger's equation has been solved for a particle in a given physical situation, the resulting wave function contains all the information in the form of probabilities except for the quantized variables about the particle that is permitted by the uncertainty principle. So once we have solved Schrodinger's equation for a particle, the resulting wave function contains all the information in the form of probabilities about the particle that is permitted by the uncertainty principle. The solution of Schrodinger's equation, the wave function of the system, can be replaced by an infinite series, the wave functions of the individual states, which are natural harmonics of each other. That is, the frequencies are related in the ratio of whole numbers. The replacement wave describe the individual states of the quantum system, and their amplitudes give the relative importance of the particular state to a whole system. Schrodinger's equation has been solved for the hydrogen atom. However, solving the equation for atoms with higher atomic numbers is still practically impossible. Schrodinger's equation has been universally accepted as one of the greatest achievements of 20th century science. It's a mathematical tool of unprecedented power for dealing with problems of the quantum mechanical model of the atom. It is important to note that the wave function in Schrodinger's equation spreads out with time. It is widely accepted that matter exhibits both particle and wave property. However, Schrodinger soon began to suspect this view. He wanted to go back to the classical idea of waves. He started to believe that waves alone can describe everything, particles were useless. Schrodinger proposed that a particle is just a wave group with small dimensions in all directions. However, Lorentz pointed out that this wave would spread out with time and cannot describe particles. Just for a bit of background information. Different models for studying quantum mechanics. The simplest model to study quantum mechanics is a particle trapped in a box with infinitely hard walls. That is the walls of infinite potential energy, infinite potential well. Ignore for now that such a system doesn't exist in reality. The particle's motion is specified along the x-axis between, say, x equals 0 and x equals L by the infinitely hard walls. The particle will not lose energy on colliding with such walls as the walls have infinite potential energy. Thus, the total energy of the particle remains constant. Thus, potential energy, say U of the particle, is infinite on both sides of the box while it is constant, say 0 inside the box. As a particle can't have an infinite potential energy, it thus cannot exist anywhere outside the box. So for x less than equal to 0 and x greater than equal to L, that is for outside the box, the wave function of the particle psi equals 0. This is known as the boundary condition. The example of a potential well with infinite walls is considered initially only for the ease of calculation. But of course, it cannot be realized in practice. In practice, you cannot have a box with walls with infinitely high potential energies. Thus, a more realistic model is a finite potential well. Let this potential well be U units high, I units wide, and contain a particle whose energy is E less than U. So as E is less than U, classical physics would predict that this particle can never get out of the box and only bounce off its walls of finite potential energy this time. But quantum mechanics predicts otherwise. The particle does bounce back and forth, but with a certain small but non-zero probability of penetrating through the walls of the box outside. Relativistic quantum mechanics. The Schrodinger equation is based on non-relativistic mechanics and thus doesn't work for cases when the modifications demanded by relativity become significant. That is, say at near death velocities. Now, if you are not aware, it's not possible for me to go into relativistic mechanics, go into relativity, special and general relativity in this video. So especially this is all you need to know is special relativity, because here we have discussed Klein-Gordon equation and Dirac equation. So that is all of special relativity, because quantum mechanics and general relativity has not yet been unified. That is a great question. So, but by relativistic quantum mechanics, we are only talking about special relativity and quantum mechanics. So if we take into account the relativistic mass energy momentum relation, E square equals m square c to the 4 plus p square c square, using the energy and the momentum operators. So there are some quantum operators, like the energy operator, that's IH cut del over del t, that is energy operator. Then we have the momentum operator. So these operators, and we multiply both sides by the wave function and simplify, we get the Klein-Gordon equation. But the Klein-Gordon equation doesn't take into account the spin property, which is accounted for by the more accurate Dirac equation. Also, the wave function in the Klein-Gordon equation cannot be interpreted as a probability amplitude. Dirac modified the Schrodinger equation by taking into account special relativity. This remains the first true version of a quantum field theory. The Dirac equation interestingly predicted the existence of matter with the exact same properties of known matter, but with an opposite charge, that is antimatter. So Dirac's theory predicted the existence of matter called antimatter, which is same to known matter, but with an opposite charge. And there are some other differences as well, but we'll not go into that here. Dirac found both forward and backward propagating solutions to his equations. This idea would be crucial in his prediction of antimatter. So Dirac's theory required that an electron can have negative as well as positive energies. When the relativistic formula for the total energy is applied to the electrons, both the negative and positive roots are acceptable. But if negative energy states going, so this is again without, like it's not possible to explain this. This is much conceptual, but I'll just read through it once in the hope that you get some idea. But this video is already very long. I don't want to make it longer. Anyway. So, but if negative energy states going all the way to E equals now minus infinity are possible, then the question arises that what keeps all the electrons in the universe from ending up with negative energies? The existence of stable atoms is in contradiction to this. Dirac suggested that all negative energy states are normally failed. The Pauli exclusion principle, named after Wolfgang Pauli, prevents any other electrons from dropping into the negative states. However, if an electron in the Dirac sea is given enough energy by absorbing a photon of energy hf greater than 2 mc square, it can jump out of the sea and become an electron with a positive energy. So in this way you can explain the existence of antimatter with electron, that is positron, electron with positive energy. No, sorry. Electron with positive energy means the electron I'm talking about. Positron is the electron with positive charge. Antimatter. I just confused it a bit. Sorry about that. So a hole is created in the process in the negative energy electron C. This particle behaves as if it has a positive charge, and this is how we get a positron. The result, so the positron is the hole that is created. Somewhat similar to the hole in semiconductors, but not exactly. The result is the materialization of the photon into an electron-positron pair. Like the electron, all other elementary particles have their antiparticles too. Interestingly, the neutral pion and a few other particles are their own antiparticles. So there is also another and perhaps more elegant interpretation of the negative energy problem. The Feynman-Stackelberg interpretation assumes that the antimatter can be treated just as matter traveling back in time. So this gives rise to a lot of metaphysical questions, but but mathematically it's a beautiful, elegant theory. It works mathematically. So matter just traveling back in time is antimatter because the equations work. If we just make some modifications that the matter is traveling back in time, the equation works. The equations work. The Dirac theory is not a very elegant interpretation. The second interpretation, though strange, is actually the better one. The quantum mechanical model of the atom. In the modern quantum mechanical model of the atom, the concept of distinct orbitals has been replaced by the concept of orbitals. Distinct orbits has been replaced by the concept of orbitals. As per Heisenberg's uncertainty principle, the position and momentum of an electron cannot be both known with 100% accuracy. Thus, the fact that Bohr could calculate both the atomic radius and the velocity of an electron can only be accounted for by the fact that the results are not 100% accurate. Thus, the idea of stable fixed orbits around which the electrons are revolving was discarded. An orbital basically represents the region around the nucleus of the atom where the probability of finding the electron is maximum. It's a sort of spread out orbit, like not fixed like the orbit. It's the region around the nucleus of the atom where the probability of the finding the electron is maximum. Electrons are treated as stationary waves, meaning that they can vibrate between the nucleus and the boundary of the atom. As we saw, the square of the wave function gives the probability of finding an electron at a particular region. If we plot a graph of the square of the wave function versus the distance from nucleus, we will see that with increasing distance from the nucleus, the probability of finding the electron reduces drastically. However, we still can't define a particular size of the atom, since no matter how small, we still have some non-zero probability of finding an electron considerably far away from the atom. So even very far away from the atom, we have a certain non-zero probability of finding electron. So we cannot define the size of the atom, definite size, like this is the boundary of the atom, the electron cannot go beyond this. We cannot define like that. The shape of the orbital is actually the approximate shape that is formed by plotting all the points produced by observing the position of an electron many number of times, where each position point represents the region where the electron is found, corresponding to this graph. Quantum numbers. The solutions of the non-relativistic Schrodinger equation for the hydrogen atom are a set of wave functions described by three quantum numbers n, l, ml. These wave functions are called atomic orbitals. However, to completely describe an electron, a fourth quantum number, the spin quantum number, is required. Every electron can be thought of to be rotating on its own axis, either clockwise or anticlockwise. Three quantum numbers are necessary to describe the special distributions of electrons in an atom. But for this property, a fourth quantum number, the spin quantum number, is necessary to completely describe an electron. Spin is an inherent property of the electron, and it's a complex property which has no analogy in classical physics. So the electron is not exactly rotating, though that's a state to make you understand. The spin of an electron can be either positive half or negative half. An orbital can accommodate two electrons, one with up spin and the other with a down spin. According to Pauli's exclusion principle, no two sets of electrons in a single atom can have exactly equal sets of four quantum numbers. So every electron has a unique set of those four quantum numbers which can completely describe the electron. So no two sets of electrons in a single atom can have exactly equal sets of four quantum numbers. That is the exclusion principle. This explains a lot of things actually. Semiconductors. Now we're just discussing some applications of quantum theory. Okay. You see semiconductors, LED, laser, and superconductors, and quantum computers. Okay, semiconductors. Let's first consider the modern theory of semiconductors. There's a band theory. Energy is needed to create electron-hole pairs. A hole basically refers to the region where the electron is absent. It behaves like a positive charge. In semiconductors, electrons can jump from the valence band to the conduction band when given enough energy. In some materials, the thermal energy at room temperature is enough to kick some electrons into the conduction band. Such materials act like semiconductors. Semiconductors can also be doped with atoms, impurity atoms of certain elements to get the desired results. If a silicon atom is replaced with an arsenic atom in a silicon crystal, we get a free electron, N-type semiconductor, N indicating the presence of an extra negative charge. Since the outermost shell of an arsenic atom has 5 electrons, out of which 4 take part in covalent bonding. If we use a material whose outermost shell has 3 electrons, then we get a whole, P-type semiconductor. The PN junction diode is a highly important device in the electronics industry. So what is the PN junction diode? We actually, when the P-type semiconductor and N-type semiconductor, they are brought close together, they interact, and a depletion region is formed, and these things take place. So that is a PN junction diode. Means basically, it from there we can make all this stuff, these Zener diodes, all this LEDs and everything, and then we have the rectifiers and many things. So it's all very important, very much application out there. It's very much practical. LED, as we already know now, energy is needed to create an electron hole pair. Energy means photon. A photon can turn into an electron hole pair, and that can happen. An electron hole pair can annihilate. That's the electron positron pair actually, but in the case of electron hole pair also, energy is needed to create an electron hole pair. When an electron and a hole recombine, this energy is released, somewhat similar to the electron anti-electron or electron positron annihilation. In some elements like silicon and germanium, the recombination energy is absorbed by the crystal as heat. However, in some semiconductors like gallium arsenide, the recombination energy is released in the form of a photon. Gallium arsenide is used in the making of light emitting diodes or LED. In LED, photons are produced by spontaneous emission. The opposite occurs in a solar cell where a potential difference and thus electric current is created. Laser. 3 kinds of transition involving electromagnetic radiation are possible between two energy levels. If an atom is initially in the lower state, it can be raised to the higher state by absorbing a photon, that is stimulated absorption. An atom from the upper state can drop down to a lower state by emitting a photon, that is spontaneous emission, and an incident photon may cause a transition to stimulated emission. Here the radiated light waves are exactly in phase with the incident ones, and thus the result is an enhanced beam of light. The concept of stimulated emission forms the basis of the working of laser technology. Unlike in an LED, when the current is high, spontaneous emission may not be able to keep up with the rate of arrival of electrons and holes in the depletion region. I know all this it makes no sense, because if you're not aware of the basic things about semiconductors and PN junction diodes and everything, it's not possible to explain it. But I just tried to make some notes so that to give you the idea, and so that to hand you with some terms in case you are interested to study further, in case you don't know, and in case you know, you can definitely relate, right? So this results into an inversion, which is the condition for laser action to occur, which spontaneously emitted photons, causing avalanches of additional photons by stimulated emission. In a semiconductor laser, opposite ends of the PN junction are made parallel and partly reflecting. The coherent light produced due to the stimulated emission is intensified as it moves back and forth in the thin depletion region and emerges through the ends. Laser actually stands for light amplification by stimulated emission of radiation. To achieve an energy density equal to that in some laser beams, a hot body would have to be at a temperature of 1030 Kelvin. The laser technology works due to the presence of one or more excited energy levels in atoms whose lifetimes are greater than usual. Superconductors. Another important technology worth mentioning is the superconductor. The resistance of some conductors drops drastically at low temperatures, and below critical temperature becomes zero. Resistance means when the electrons are flowing, that gives rise to an electric current. But this electric current, the material through which the electron is flowing, obstructs the flow of the electron, offers some resistance, and this resistance is usually enemy to the flow of the current. So the resistance of some conductors, however, drops drastically at low temperatures, and below a critical temperature it becomes zero. That means unlimited current, superconductors, right? Because the resistance has become zero. The BCS theory, Bardeen, Cooper and Shriver theory, theory of superconductivity, explains the phenomena in which a current of electron pairs flows without resistance in certain materials at low temperature. This can happen when a single negatively charged electron slightly distorts the lattice of atoms in the superconductor, drawing toward itself a small excess of positive charge. This excess in turn attracts a second electron. This attraction binds the electrons together in a Cooper pair, and in this way you can, like, the resistance drops up to zero. Like superconductivity can be explained. Superconductors can either be type 1, which stops exhibiting superconducting behavior above a certain critical value of magnetic field, or type 2, which has 2 critical values of magnetic field and behaves like a superconductor and yet have a magnetic flux, for no magnetic field normally exists in a superconductor. Why can't a magnetic field exist in a superconductor? An applied magnetic field can exist inside a superconductor at temperatures above its critical temperature, when it doesn't act like a superconductor. However, when the superconductor is cooled below the critical temperature, surface currents appear whose effect is to expel the magnetic field from the interior of the superconductor. Meissner effect. This property has been exploited to levitate superconductors in the presence of external magnetic field. This forms the basis of the maglev magnetic levitation train technology. So, like, the high speeds, no friction and all these things, very useful. Recently, certain ceramic materials have been shown to exhibit superconducting behavior. Research is going on to increase the critical temperature to an easily attainable value, because the critical temperature is very low, so we cannot go down to such low temperatures. But if it's a attainable value, then we can easily create superconductors, right? Since attaining such low temperatures remains difficult. Other problems, like the fact that ceramic crystals are brittle and difficult to make into wires, cannot carry high currents, and tend to be unstable over long periods, need to be overcome if superconductors are to revolutionize the electronics industry. Quantum computers. Superconductors are used in building quantum computers. Recently, interest in quantum computing has risen, and many companies are investing huge sums of money in this technology. Quantum computing is basically a new way to store and process information based on the principles of quantum mechanics. Classical computers store information in binary bits, zeros or ones, but quantum computers store information in qubits or quantum bits. A qubit can be both 0 and 1 at the same time, just like superposition. And a series of qubits together remember many different things simultaneously. With the advancement of quantum computing technology, it's expected that the size of these computers will decrease, and they will be able to function efficiently at room temperatures. To build a quantum computer, you need to get the system in a superposition state. You can do this in a number of ways. In superconducting loops, a resistance-free current oscillates around a circuit loop, and a microwave signal excites the current into superposition states. You can also trap an ion and excite it into superposition state. You can manipulate the quantum state of an electron, etc. There are a number of technologies like silicon quantum dots, topological qubits, etc. It should be noted that quantum computers are highly sensitive, and surrounding noises can break the superposition state and disrupt the functioning of the computer. Charges, fields, vibrations, cosmic rays, etc. are the sources of noise. You need to either reduce noise or make the computer insensitive to noise, or maintain active quantum error correction. Okay. Okay, so quantum entanglement. In quantum mechanics, the idea of entanglement is highly important. Consider a spinning particle having two possible orientations, up and down. The wave functions thus would be psi up and psi down. Let the spin state be given by psi s equals alpha psi up plus beta psi down, where alpha and beta are complex numbers. Let the measurement of the spin orientation be performed by measuring device D. D is also a quantum system which has two possible wave functions, psi d up and psi d down. The detector gets coupled to the system in such a way that when the spin is up, the detector wave function switches to psi d up even if its original state was psi d down before coupling to the system. The same thing happens with the cat's alive and dead state, and respectively the radioisotope's non-decayed and decayed state in Schrodinger's cat paradox. See later. Hence, because of system detector coupling, this combined wave function becomes psi s, d equals alpha psi up d up plus beta psi down d down. Alpha psi, d is a state which is a coherent superposition of two possible states. It is during the measurement process that as further reduction occurs and the coherence is lost, and system detector combination gets reduced to the two individual states, psi up d up and or psi down d down, with the relative probabilities alpha squared and beta squared. As per the widely accepted view, this last reduction happens because of the interaction of the system with the environment, which in turn happens inevitably and uncontrollably whenever there is a measurement. Everything exists as a superposition of all possible states until observed. On observation, only one state is revealed. So this last reduction, the collapse of the wave function, that happens as per the widely accepted view, that happens because of the interaction of the system with the environment, which in turn happens inevitably and uncontrollably whenever there is measurement. So this is a crucial point. Now, as I promised you, I will be coming back to the E-pair paradox. So here's the E-pair paradox. Consider two electrons with opposite spins. Electrons which are coherent and belong to the same quantum system initially must have opposite spins. Recall Pauli's exclusion principle. If there are two electrons in the same orbital, all in the quantum numbers except spin would be same. So the spin of the electrons must be opposite, since there is a unique set of 4 quantum numbers for each electron. If such an entangled pair of electrons is released from a common source in opposite directions at near light velocities, over time the electrons may reach opposite ends of the universe. But we know that the spin of the electrons is undefined before they are observed. If undefined in the sense the spin of the electrons or any parameter actually exists in a superposition of many possible states. Only in observation it collapses to a particular state. So before we observe the spin is in a superposition of both up and down state. If an electron is observed when it is already far away from the other, say light years away, its spin will collapse from a superposition of up and down states to a distinct state. At that instant, the other electron spin must also, without direct observation, collapse to the opposite spin. Some information passes between the electrons faster than light, violating causality. So this was the paradox. As per the classical idea of locality, no remote event can affect a particle in any way. The impact may propagate and enter the local environment, but never with a velocity greater than the speed of light. It cannot occur instantaneously. According to Einstein, Podolsky, and Rosen, EPR, a sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without in any manner disturbing the system. Bohr, who had already refuted Einstein's previous arguments against quantum mechanics, pointed out that without in any manner disturbing the system is in itself impossible due to the inevitable interaction between the object and the measuring instrument. In fact, according to Bohr, the act of measurement is fundamentally crucial. It can even change the properties of the object being measured. Bell's inequality. Is nature non-local? Things can indeed remain entangled through space and time. Many physicists assume that there were some hidden variables yet to be discovered, and once they were discovered, all the bizarre ideas of quantum mechanics would then, when interpreted along with that, become acceptable again. The idea was that local hidden variables already carry the information about the particles, say the spin. But John Bell has mathematically proved that there can be no hidden theory compatible with quantum theory. Bell's theorem has been repeatedly verified experimentally. Things separated through space-time can in fact remain entangled. Let's say we have some particles and we subject them to 3 tests, say A, B, and C. In each test, the outcome can either be pass, say 1, or fail, 0. There are 8 possibilities. Also, in 2 of the cases, the outcomes of test A and B, that is AB, test B and C, BC, and test A and C, AC, are the same S. In the other 6 cases, either AB is same and BC and AC are different, or only BC is same and only AC is same. It is clear that at least 1/3 of the time we must get the same outcome. So all this didn't make any sense to you, I know that. So here's the table. So test A, test B, test C. So how many possibilities are there? So for each test, it can either be a 0 or it can be a 1. So we know how to fill this kind of table, right? For test A, first 4 zeros, then 4 ones. Then for test B, 2 zeros, 2 ones, 2 zeros, 2 ones. Then 0 1, 0 1, 0 1, 0 1. So 0 0 0 is one possible combination. 0 0 1 is one possible combination. 0 1 0, 0 1 1, and like this we have 8 possible combinations. 8 possible possibilities. So AB means whether A and B are similar or not. So in this case, test A and B both are 0. So both are similar. BC is similar, AC is similar. All 3 are similar in this case. AB is similar in this case, 0 0. But BC is 0 and 1, different. So like this we can write for similar and different for all these cases, for AB, BC, and AC. So you see, in all the cases, at least 1/3 of the case there is similar. Like here we have at least 1 S. Here also we have 1 S, 1 S. Here also we have 1 S, 1 S, 1 S, and here we have 3 S, and here also we have 3 S. So for at least 1/3 of the cases, we get similar results, right? Simply put, if we fire photons in pairs from a source in opposite directions to 2 observers who can randomly select any one of 3 different polarization filters and see whether the photon passes through it or not, then Bell's inequality tells us that both of them should get the same result at least 1/3 of the cases. However, repeated experiments have revealed otherwise. To derive his inequality, Bell used certain facts and ideas with which everyone could agree, except for Einstein's condition of locality, which he assumed to be true. If experiments show that the inequality was violated, that would mean that one of the assumptions in his derivation was false. Bell chose to interpret this to mean that nature is non-local. There have been many experimental verifications of the violation of Bell's inequality. This has been argued to mean that, in spite of local appearances of phenomena, our world is actually supported by an invisible reality which is unmediated and allows instantaneous, faster than light communications. So this actually can explain a lot of things like parapsychology and stuff, but we'll be explaining that near the end of the video. So these interactions don't diminish with distance and can link up locations without crossing space. Actually, there is nothing spooky with the concept. We who are used to classical mechanics might find it bizarre. The key is that entangled systems, no matter spanning how much distance, are described by a single wave function in quantum mechanics. But it must also be noted that the results of these experiments are not 100% foolproof. Einstein's battle against quantum mechanics. Amid the chaos of the Second World War and the then new quantum mechanics heresy, Einstein would remain engaged in a futile attempt to unify gravitation with electromagnetism, using geometry alone. So in my recent blog about the theory of everything and consciousness, I've described this Kaluza-Klein concept, Einstein's battle, and string theory, and loop quantum gravity and quantum gravity theories. So amid the chaos of the Second World War and the then new quantum mechanics heresy, Einstein would remain engaged in a futile attempt to unify gravitation with electromagnetism without using geometry alone. He would keep this up for over 30 years until his death. He couldn't bring himself to truly accept the strange, bizarre ideas of quantum mechanics. He believed in the perfectly ordered and deterministic universe, putting up his famous mantra against quantum randomness. God does not play dice with the world. God must, according to him, follow certain fundamental laws according to which the universe functions. Bohr, however, retorted with, "Stop telling God what to do." Einstein believed in an objective reality. An important question regarding quantum mechanics is whether the reality is subjective or objective. Quantum mechanics may be observer dependent. However, this is an extremely sensitive topic and is prone to be misunderstood. As of yet, the debate between realism and solipsism hasn't yet been conclusively settled. Maybe the world exists independent of our observations, or maybe the observation matters and the reality is subjective. Rabindranath Tagore visited Einstein in 1930. They had a conversation on whether the reality is subjective or objective. Yes, all we can account for is the existence of our subjective reality. We cannot get out of our consciousness to see if there's an objective reality out there. In fact, there is no way to prove that the reality is not just ideas in our minds. Actually, this is true. It is of utmost importance to realize that a subjective reality can create the illusion of an objective world and vice versa. So maybe there is no definite answer to the question of whether the reality is subjective or objective. QM is incomplete, but not wrong. The journey of quantum physics has been a long and inspiring one. Maybe Einstein is correct in saying that quantum mechanics is incomplete, and we need a deeper theory for a better understanding of nature. However, it is also worth pointing out that quantum mechanics cannot be wrong. Quantum mechanics has survived many stringent tests, theoretical and experimental, and it works surprisingly well. It works. Maybe we encounter paradoxes if we try to go too deep into it, but still, I repeat, quantum theory works. Thus, it can be the case that quantum mechanics is incomplete, but it can never be just plain wrong. Quantum randomness and Schrodinger's cat. While Einstein questioned the completeness of the quantum mechanical description of reality, Schrodinger devised his famous cat paradox. If a cat is kept in a box under conditions such that it has a 50% chance of living and the same of dying, and this was made solely dependent on some other system, say a radioactive substance attached to a Geiger counter, such that if it decays, the counter will trigger a hammer to break a poison bottle and kill the cat, and otherwise not. Basically, the experimental setup is really simple. Like, you have a cat in a box and you have a radioactive element. So that radioactive element can decay or it cannot decay. That is purely probabilistic. You cannot predict whether it will be decaying or not. If it decays, then it triggers off some reactions which ends up opening a poison bottle and killing the cat. And if it does not decay, then the poison bottle is not opened and the cat lives on. That's all. Then the quantum states of the cat and this system become entangled. When you take into account the characteristics of radioactive decay, quantum mechanics predict that the cat must both live and die at the same time before it is observed. A similar thought experiment emphasizes gunpowder exploding and not exploding at the same time. Only after observation we find the cat to be either dead or alive. This only shows that either the other possibilities that are not fulfilled in the universe are fulfilled elsewhere in a parallel universe, like Everett's many worlds interpretation, or that direct observation is required to collapse the cat's wave function from a superposition of states to a distinct state, Bohr's Copenhagen interpretation. So only after the observation we can find the cat to be either dead or alive. After observation, the wave function collapses. We see that either the cat is dead or the cat is alive. But before observation, according to quantum mechanics, the cat must be both alive and dead at the same time. So this shows that either the other possibilities, like if the cat is dead in this universe, maybe it is alive in some other parallel universe. Then the other possibilities are not fulfilled in this universe are fulfilled elsewhere in the parallel universe. Or that direct observation is required to collapse the cat's wave function from a superposition of states to a distinct state. This is Bohr's Copenhagen interpretation. The cat may itself perform this act of observation. This is all speculation, just to say. So maybe the intensity of the observation matters. Otherwise, one could say that the cat initially capable of observation must always live on in the above thought experiment. Also, it's important to note that in this thought experiment, the cat should never be allowed to physically interact with the system of the radioactive substance in the Geiger counter connected with the hammer and poison bottle. Copenhagen interpretation of QM. Okay. The Copenhagen interpretation of Schrodinger's cat thought experiment suggested that it is observation that collapses the wave function of a particle from the superposition of all possible states to a single distinct state. But does it give a satisfactory explanation as to why a particular state among all the possible states should be observed? The entire thought experiment is based on entanglement, superposition, and measurement. Entanglement implies that an entirely new and single quantum system has formed. As soon as you open the box containing Schrodinger's cat and peek into it, we ourselves get entangled with the system. If we see the cat alive here, it means that different versions of us in a parallel universe see the cat dead, and so on. All possible states must manifest themselves. It follows that constantly with the evolution of time, new worlds are being created, branching off from the previous worlds. This sounds crazy. It may even be the case that an infinite number of universes are present and the infinite possibilities that take place in them. All just speculation, once more. But yeah. What about consciousness? According to the Copenhagen interpretation, nature is intrinsically probabilistic. In his Copenhagen interpretation, Bohr could never specify exactly what counted as observation. Do we need conscious beings to do the observation? But then what is consciousness? How can we come up with a rigorous definition of consciousness? To resolve this problem, some have suggested that we are living in a computer simulation. The computer doesn't calculate the exact properties of a particle until it is relevant to and observed by the player, simply to save energy. For instance, in video games, details of the surroundings become prominent only on zooming in. Just like that, only on direct observation are we aware of the exact properties of the particle, not before that. Again, from this point forth, everything is speculation. Just a warning, so take everything with a pinch of salt. Wave function collapse. However, the question remains how exactly the wave function collapses. Objective collapse theories propose that wave functions have a small chance of collapsing on their own at each moment, without observation. If there are many entangled particles in a system, then the chance of collapse increases, since if a single particle collapses to a particular state, the other entangled particles, and as a result, the entire system will collapse to the same state. Others believe that interaction with space-time curvatures causes the collapse of the wave function. The latter hypothesis may fortunately be testable. Not as of now, but it may be testable in the future. Now let us consider another deep question. When a wave function collapses, it must collapse everywhere simultaneously. This means that it is possible under certain circumstances for information to travel at a speed greater than the speed of light, as we saw in the EPR argument. This means theoretically we could send information back in time. But the idea of retrocausality views all this from a different perspective. It is indeed not possible to travel faster than light in space, but particles may travel backward in time. Indeed, antimatter is indistinguishable from matter traveling back in time. Two particles may communicate with each other through time, not space. This idea might seem appealing to many, and it has its advantages, but as always, problems remain. Transactional interpretation. According to the transactional interpretation, the wave function moves forward in time while its complex conjugate moves backward in time. It is a transaction between these two wave functions that let the universe decide which path to select independent of any observer. Does this mean that the future is predetermined? No. The wave functions traveling backward in time are traveling from possible futures rather than a future which is completely predetermined. So all these are philosophical interpretations of quantum mechanics. Superdeterminism. Speaking of determinism, the concept of superdeterminism holds that everything was always predetermined and this information was transmitted to all the particles during the Big Bang. In contrast, according to quantum Bayesianism or cubism, the universe is intrinsically probabilistic. There is no objective reality, only personal beliefs. The wave function represents our personal subjective beliefs and the objective reality. There is thus no objective wave function. The collapse of the wave function is simply us updating our beliefs about future probabilities. So all these theories, these are not hardcore physics because they make a number of assumptions and there are a lot of speculation. There are a lot of metaphysics like consciousness and everything. So we cannot, and most of it is not verifiable by experiment. But still I'm discussing it. Other interpretations. Other interpretations like the relational interpretation propose that any system, whether it's conscious or not, can observe. Observers may disagree whether the system function has collapsed or not, just like in relativity observers in different reference bodies may disagree about the time when an event took place. Consider the EPR thought experiment. When the particles have reached far apart, no observer can actually measure both the spin simultaneously. From the perspective of an individual observer, the spin of the unobserved particle is still undefined until the observer interacts with something that has measured the spin of the particle. Okay. Now, so a few words are less, a few slides are left. A word on consciousness. Now this is again my personal views from this point forth, but I have evidence to back up my claims. It's not like I'm saying this without evidence. And this is all about consciousness, and it's also somewhat related to quantum physics, so it's important. So please be remembered. If you have waited for, let's see, yeah, if you have waited for 1 hour and 13 minutes, then I guess you can wait for another 5 to 10 minutes. Okay. A word on consciousness. All our present science does is explain the workings of the inanimate world from a third person perspective. But we don't really know how our consciousness gives rise to the perception of this beautiful world, or how consciousness emerged in this world. If by science you mean just explaining how the inanimate world works, you are leaving out important bits of the story. It may be true that we are limited by our consciousness, and there is a saying that if the brain was simple enough to be understood, we wouldn't be smart enough to understand it. But we need to understand consciousness. We need to expand the scope of science. Some people will say it is pseudoscience. Metaphysics is useless really. But no, we have to break out of this materialistic view of science. Is consciousness just emergent from matter? Consciousness very likely is not just an accident of combination, and although human consciousness likely emerges from complex interactions with the brain, there is more to consciousness. It would perhaps be better to say that human consciousness manifests through complex interactions in the brain rather than emerges from the same. Consciousness is a fundamental phenomenon. As Shoni just says, consciousness cannot be accounted for in physical terms. For consciousness is absolutely fundamental. It cannot be accounted for in terms of anything else. and the human consciousness is linked to this fundamental consciousness in some way. This is likely to be true because this explains a lot of parapsychological phenomena like non-local perception. I will not go into whether these phenomena are true or not, but evidence says yes, they are true. And what we treat as pseudoscience today will likely be a part of science tomorrow. Mind and matter. This is the same thing basically I'm discussing. We have so far kept consciousness outside mainstream science. As I've already said, our science describes the world from a third person perspective. We know how inanimate objects work and everything, but most scientists ignore the fact that it is through our consciousness that we perceive everything. In Mind and Matter, Schrödinger writes, the world is a construct of our sensations, perceptions, memories. It's convenient to regard it as existing objectively on its own, but it certainly doesn't not become manifest by its mere existence. It's becoming manifest is conditional on very special goings on in very special parts of this very world, namely on certain events that happen in the brain. That is an inordinately peculiar kind of implication, which prompts the question what particular properties distinguish these brain processes and enable them to produce a manifestation. Can we guess which material processes have this power, which not? Or simpler, what kind of material process is directly associated with consciousness? Consciousness is fundamental. This is what I'm trying to say. It is all very well to say that consciousness emerges from the brain, only that the brain is not the seat of the consciousness. Science must learn to look beyond the brain. Evidence shows that consciousness in near-death experiences persists even in absence of brain activity. This shows that consciousness and the brain are not interdependent, not to a very great extent. As stated above, consciousness, more specifically human consciousness, manifests through the brain, but does not, it is very likely, emerges from the brain. Consciousness can be thought of as a more fundamental and all-encompassing phenomenon of our universe. Quoting Sir James Jeans, the universe begins to look more like a great thought than a great machine, rather than just an accident of combination, or in other words, a consequence of complex arrangement of matter. Parapsychology, consciousness, and quantum entanglement. There may also exist many levels of consciousness, and interactions between these levels can explain ESP or extrasensory perception, phenomena like telepathy, precognition, etc. Hitherto, we have treated such phenomena as unreal and pseudoscientific, but the mounting evidence says otherwise. Parapsychology is indeed an emerging science, and I believe we will have to accept the existence of parapsychological phenomena gradually. The possibilities are endless. All we need to do is remain bold enough to explore them. Interestingly, quantum entanglement might explain the entangled nature of reality and how non-local perceptions and interactions, extrasensory perceptions, are possible because it can happen instantaneously. Once more, these phenomena are not unreal. There is evidence of the contrary. We just need to grow out of this materialistic and narrow phase of science. So that is all I wanted to say in this video. I hope I gave you a basic awareness of what quantum science is all about. And once more, happy Quantum Day to all of you. Thank you. Please comment below, like, share, and subscribe to the channel. Thank you very much.